Okay, so this has just got a little bit of information about what the course is and some contact information. Um, if you click this button that says get started, it'll take you through, instead of just a single page syllabus, I kind of broke it out. There are a few different tools that we'll be using. One of them is obviously Zoom, which everybody's got figured out. And I think about 15 people have figured out getting into Piazza. And you can access Piazza directly from the link that's in the left navigation pane over in Canvas, but I recommend just going to Piazza directly so that it doesn't look so like nestled in here. You know, you can just open up the website separately and have the full page. Let's see. So the other thing that we're going to be using this semester, that's our web-based textbook, Zybooks, and I put a little video tour of that in Canvas, but let's see. So if you just go to zybooks.com and create an account, then you'll be able to buy the book if you haven't already. I see about half of the class has bought the book. If you are not sure about being in this class or in the program or something, you can do a trial. You can also buy the book, and if you drop the class, they'll refund that, you know, they'll a prorated amount for how long you've used the book. Let me see. So you've some of you have already been through a little bit of this, so you can play around with this. Each chapter has sections in it that you can click on, and there are different kinds of activities throughout the section. There's these things called participation activities, and there are also some that are called challenge activities, although I don't think there's any in the first couple sections of our textbook. And as you may have seen, if you look at the grading part of the syllabus module, you'll see that weekly reading accounts for 10% of your grade. So when you're doing your reading, you know, and reading the chapter, whatever the assignment is, you'll need to make sure that when you're doing that reading that you get all of the, this stuff is not graded for correctness. I can't see if you got the right answer, or you can click on anything you want, and all I'll be able to see is whether or not you actually did that activity. All right, so it's not graded for correctness. So that weekly reading is accounting for 10% of your grade. Every week there'll be starting next week, not this week, there'll be a short quiz that will be graded for correctness. And then there'll be 3 exams. So exam 1, 2, 3, not 2 exams and a final exam. They'll all be weighted equally, and they won't be cumulative any more than they need to be. All right, so we're going to kind of chunk out the course into 3 pieces and have exam on each one of those. Does that sound good? Yeah. And I'm going to try and keep our course as straightforward as possible. I've been to a bunch of training things about about designing online courses and the kinds of bells and whistles and stuff that you can add to them. But I think it's nicer to just have it be kind of clean and mostly about the math. So we'll just keep this pretty straightforward. And I think, well, we can talk about those things later. Let me just do what I have to do for this part so we can get right to the math. You'll see, for your reference, I've put up a schedule for the semester. This is, you know, obviously subject to change in case something happens or we need to spend an extra day or 2 on a specific topic. But you'll see that I've scheduled an entire week for each of the exams. And that is because I like to have a few days to do review and stuff. And also because people are all over the world and this is online, I'm going to give you a window of a couple of days to take the exam. There'll be a time limit. So once you start, you'll need to finish the exam in a certain number of hours, but you'll be able to access it for 2 days. Okay. More about the exams when we get there, right? The first one isn't for a month. And then we are required to list out some course learning outcomes. So if you want to see kind of the things that we're going to cover this semester, there's a list of them right there. Let's see, what else did I want to address specifically? Many of you have already been over to Piazza and introduced yourself. If you haven't yet, please do that. I and your colleagues are very interested to know you. You guys are a cohort, right? You're in this program, all of you together. And I think this is the first class you've had, and then you have a meeting with Chris Brooks, right, for your other course after this. So you guys should like schedule happy hours and stuff together. It'll be fun. In the other groups that I've known that have come before you have really been, they've gotten to be like really tight because it's a lot of hard work. All right, and so this last thing that I need to just point out that this is part of the template that the university gives us for the online courses, is this stuff about netiquette and accessibility and, you know, just policies and honor code and stuff. And you do need to, this little icon right here that looks like a rocket ship is a quiz, and you do need to take this one. This is the honor code quiz that everybody takes, and it's basically just, you know, you sign and say you're going to read the honor code policy and follow it. So please go ahead and do that. So coming to you later today will be a poll about times that would work for you for me to have office hours and for us to have extra problem sessions and stuff if anybody has specific questions. So that I can, you know, I know everybody's all over the place, so I can set times that work with all the time zones. Before we start with the actual material, I kind of want to paint the big picture for you. And that is that I kind of think of this class, the material that we're going to cover in two parts. One of the parts is what I call low level, and the other one is called high level. And that's not to mean easy and hard. You may have heard people talk about low-level programming languages and high-level programming languages, and that's the kind of low and high I'm referring to. So in programming languages, low level is like assembly and machine code. And high level is things like Python, maybe Java. In between stuff would be things like C++ and like Fortran and things. But I'm just gonna break it into two sections. The low level stuff, well, let me start with the high level stuff. So if you've taken some math classes, you've probably taken things like calculus, maybe like an algebra 2 class, or a geometry class. And things like graph theory, probability. Most of the stuff that people think of as mathematics is really what I would put in the category of high-level math. The low-level mathematics are things like logic and set theory and proof. And these things kind of provide the language and rules that we need to do all the rest of this high level mathematics, right? So in order to have a formalization of, you know, dynamics by using calculus, we have to have kind of agreed upon rules and agreed upon language to discuss all those things. Oh, by the way, this lecture is being recorded, and also, obviously, I'm writing notes on a computer. So I'll make these notes available to you as a PDF, and I'll also put a link up to the recording when we finish, okay? I should have mentioned that earlier. Anyway, so we've got this high-level part. that we will cover some of later in the course. We'll talk a little bit about graph theory and possibly even a little bit about probability. We'll be doing things like algorithm analysis. Which I would also consider high level. And this is, we'll be thinking about time complexity, which is a super interesting kind of analysis to make of an algorithm. But that's much later in the semester. This is where we're going to start. With the low level stuff. And the reason that we do that is because what we need in order to do the high level stuff is a formal language. And the formal language that we're going to develop is the one that computers use, right? So we're going to develop a formal language that can be processed by a machine. And by formal language, we mean something that is never ambiguous. So, you know, in human languages like English and Chinese and every other human language, there is some ambiguity. Just when we're expressing ideas and things, there's non-unique interpretations for strings of words in human languages. In a formal language, there will be no ambiguity. And it's really, you know, precise and exact in what that language is expressing. Okay, so questions so far? Again, please don't worry about interrupting me. Just unmute and ask a question if you have one. Let's see, I just realized I put this slide in the wrong order. Okay, so we'll start off. So our goal is going to be to develop what we call first order logic. And right now we don't have all the jargon that I need to explain what the difference between first and second and other higher order logics is, but we will have that. But that's our goal, is to develop what we call first order logic. And the first step is to put together a language that's called propositional logic, or sometimes sentential logic. I'm spelling that wrong. Propositional or sentential logic. Can you guys hear me okay? Is there like a loud fan noise or anything? I have another mic here that I can use. Maybe it's better.
It sounds good to me.
It does sound okay?
Yeah.
I feel like the fan sounds really loud to me. So, all right. All right, so propositional logic. So propositional logic is a pretty, it's a nice place to start. It's not super expressive, so we can't say a whole lot of things, but it plays an absolutely essential role in all of mathematics at this very, very low level, and certainly in computer science. So there are basic parts, and the basic building blocks of all the things that we'll do in propositional logic are things called propositions. You can also think of them as assertions. And these are just declarative sentences that have what we call a truth value. Spelling is really not my strong suit, so apologies in advance for that. So these are declarative sentences that have a truth value. And having a truth value means they are either true or false. So let me give you some examples. Let's start in English, and then we'll write some things in math. So here's one. And so this says, you know, Obama was president in 2011. And that's a declarative sentence. It does indeed have a truth value, right? And we happen to know what it is. Here's another one. So that's an expression in mathematics, but it is a sentence, right? If you read it out loud, it says 3 + 1 = 4. It makes an assertion. That assertion happens to be true. Here's another one. 6 is greater than 7. Again, a sentence in mathematics, right? That happens to be, I guess, false. And let's see. Oh, how about this one? So Goldbach's conjecture is true. Anybody know what Goldbach's conjecture is? No? This is a good one. It's one of the most famous unsolved problems in mathematics, and it's totally an aside, but it's a problem from number theory. It says that every prime number greater than, I said prime, but I meant even number, greater than 2 is the sum of 2 prime numbers. And nobody knows if this is true or false, but it is either true or false. So it certainly would count as a proposition. Even though the truth value is unknown, it still has a truth value. Does that make sense? Okay. Yeah, so that's an interesting one to read about if you're so inclined. Let's see. Okay, how about some non-examples? Just to see what we're comparing to. It's nice to see something that's in the class and also out of the class. So there's lots of different ways that something can fail to have this property of being a declarative sentence that has a truth value. One way to fail to have those properties is to just not be a declarative sentence at all, right? So how about this? Right, how many prime numbers are there? This fails to be a declarative sentence, right? This is a question. It does not make an assertion that we could decide is true or false. Okay. By the way, now that I've used this number or used this word primes before, just I know it's been a long time for some people, so let me just remind you that a prime number is a number that can't be factored. It can't be divided evenly by any numbers except 1 and itself, right? So like 6 is not prime because you can write 2 times 3, but 7 is prime because the only way you can write that as a product is 1 times 7. That's all I say. Okay, so how many prime numbers are there? That fails to be what we call a proposition in our formal system that we're setting up here. Let's see, this 3 times 6 plus 7. This is also something that fails to make an assertion, right? There's no way for me to say that that's true or false. What I would say is that it's, let's see, 18 plus 7 is 25, right? So this isn't true or false, it's 25. There's no assertion here. And there's lots of ways to break this. I guess both of these are not declarative sentences. So here's a declarative sentence that fails this other condition, that it has a truth value. All right, so read that sentence. It just says this sentence is false. And ask yourself about the truth value. So just take a minute. Is that statement true or false? Can it be true?
No, it contradicts itself.
Yeah, well, yeah, so it's self-referential, right? So if it's true, then that would mean that it's false. And if it's false, then it would mean that it's true. So this is not a proposition. There is no way to assign a truth value to it. Okay. Questions, anyone? Brian, I like the Brady Bunch background very much. Okay. So far, this probably doesn't feel like, for most of you, a math class, right? Because we're not doing any algebra, and we won't. But at least we won't do any regular algebra. We'll do what we call propositional algebra. So we have these basic building blocks, and just like in regular math, you use variables and you can plug in numbers. In sentential logic, we'll use what we call propositional variables. And the idea is that we would plug in for those variables instead of, so numerical variables are often X, Y, and Z, probably you remember from ages and ages ago. Propositional variables tend to be P, Q, R, and so on. And the idea with propositional variables is that we're going to think of plugging in propositions to them. And that's the value that they take on, the truth value of that proposition we plug in. Okay, and so we're going to use these propositional variables in expressions, let me say compound expressions. And compound sentential or propositional expressions are things that we get when we take these basic building blocks and we put them together with connectives. So we will use logical connectives to build new propositions from smaller ones. I'll say old ones. And the way that we do that is by using words that you think of as being connectives in your everyday language. So the two connectives that we will treat first are and or. And another one that we'll also use today is, it's not a connective, it's sort of a it's like a unary operation. So one input, one output, and that'll be not, or negation. All right, and so the idea of how we're going to use these words is just, you know, the intuition that you have about how to use them is the right intuition, right? So we're going to take two old statements like 3 + 1 = 4 and 6 is less than 7, and just put the word and in between them. Now, this new statement that I've made from the two old ones, by connecting them with this connective, the word and, is a new statement, right? It's making an assertion itself. And what we need to do, this is also, I can also do this with or. And I could take one of these statements and say, it is not the case that 3 + 1 = 4. And in each of these situations, in these two situations, I'm using a connective to build a more complicated, larger compound statement out of two smaller ones. And in this one, I'm negating that assertion that 3 + 1 = 4. Another way of writing it's not the case that 3 + 1 = 4 is to write 3 + 1 is not equal to 4. And you're more than welcome to write that. This is probably better. Okay, so I'm using these words in English and relying on your intuition to understand what they mean, but intuition about what and or mean is not good enough in a formal language. So we need now to define what is and, what is or, what is not, what is that, what do all those words mean? So we need our formal language to formally define these words, and or not. And the way we do that is by considering all the possibilities of the two statements that we're connecting and deciding what the truth value of the compound statement will be. So again, we're going to use these propositional variables. Let's work out and first. And we have these two propositional variables, P and Q, and we think of each one of those as, we could plug in a statement that's either true or false to each one of those. And so what are the possibilities? Well, if I plug in a statement for P that's true and plug in a statement for Q that's true, then that's one possible thing that could happen. The statement I plug in for P could be true, and the statement I plug in for Q might be false. Or P could be true P could be false and Q could be true, or they could both be false. So these are all the possibilities. And we have to say exactly what and is going to mean. You could think of P and Q as, if we plugged in 3 + 1 = 4 and 6 is less than 7, then we'd be in this first case of having plugged in two true statements. And for the and situation, it's nice because it exactly follows your intuition, right? In order for a statement that says something and something else, in order for that statement to be true, both of those subparts have to be true. Either one of them is false, then the and statements will be false. And if both of them are false, then certainly that should be false. So let's just practice with that a little bit. We can take 1 + 1 = 2 and let's just keep it simple, right? 3 + 5 = 4. Is that a true statement?
False.
It's false, right? And it's false because one of its parts is false. So this is corresponding to that line of the truth table, right? Where the first thing that we plugged in for P was a true statement, and the second thing we plugged in was a false statement. Good? Okay. All right, so yeah, that's our definition of the word and in our formal language. And I have to do some notation here. Just like we use the equals sign to abbreviate the word equals, there's a notation that abbreviates the word and. But it looks like if you were going to draw a capital A for and, but you didn't put the line there, right, to make it an A. So it's like an upside down V. Okay, so now we've defined the word and. Next thing I want to do is define the word or, which is actually a little bit more complicated than it seems like it should be. So we'll start off again with two propositional variables. And we're going to be thinking about the compound proposition P or Q. And we're going to consider all the possibilities of what the truth values are of the statements that we would plug in. So both can be true. We can have a true false configuration or a false true configuration, or we can have both false. So now let's take a second to ask yourself, what do you think should be the case here? So I've made the truth value of each of the compound parts correspond to the line in the truth table that I've written over here. What do you say? Are any of these definitely true or definitely false?
Yes, I think we need to like check if at least one of them is true. So the first three cases have at least one assertion that is true.
Yeah, that's exactly right. So that's not the only option though, right? Because or in the English language can mean at least one of the things is true, or it can mean one but not both, right? And that's usually called an exclusive or. So there's two kinds of ors, inclusive and exclusive or. So for the inclusive or, which is what or means in mathematics, and that means that one or the other or both are true. So if at least one of the two statements is true that we plug in for propositional variables, P and Q, then the compound statement with the or in it is true. Both of them are false, then it's false. There is also a notion of this exclusive or, right? So that is the symbol for or, the inclusive or. It looks like a capital V. So XOR is the exclusive or, and its symbol sometimes is written as a sign with a circle around it. And the way that it is defined, so now we've defined and or, and now we will define exclusive or. And if we consider all the options, exclusive or means one or the other is true, but not both. So that's what the truth table looks like for that.
Wait, would you mind repeat that? Because your voice was a bit static earlier.
Ah, sorry. So which part? About the exclusive or?
Yeah.
Okay. So exclusive or means one or the other, or both statements. Oh, I'm sorry, but not both statements are true. Inclusive or means at least one of the statements is true. So we've defined.
Are we
Yeah.
Are we using both exclusive and inclusive or in mathematics?
Yeah.
Or
Yes, yeah. But when a mathematician is talking and they say the word or, they mean the inclusive or. So unless you specifically say exclusive or, then you just say, and it's always inclusive.
Okay, got it.
In the formal notation, you know, in our formal language, there's never any question because we use this formal notation. We always know what we're talking about, right? If I write P or Q, no or I mean, there's no ambiguity. So we define P or Q, PX or Q. We've defined P and Q. Now what I define is the negation. Because it's just maybe what you would think it is. So this is a unary operator. So really what I wrote before when I wrote it is not the case that's what we're appending to the front of a proposition when we need it. So it's not the case that 4 + 1 = 5 or whatever this propositional variable is representing. So that P is the propositional variable. And when we are reading in our formal language, when we're reading mathematics, people often just say not P. And the notation for this is, it looks like your proposition is kind of like holding a little pistol. And for negation, we define that as the following. So there are two possibilities if we just have a single propositional variable. either P is true or it's false. So if P is true, that makes not P false. And if P is false, it's not the case that it's not the case that something, that'll be true. Yeah. So that's our definition for the word not, or is not the case that. It just flips the truth value. Questions?
Oh, does negation change the initial assertion, or does it change the output of the initial assertion?
So let's see. So if P is the statement 6 is greater than or equal to 4, then not P we could write in different ways, right? You could say it's not the case that 6 is greater than or equal to 4, or we could write something like this. Or since we know that greater than or equal, we know what greater than or equal to means, we could write this means that 6 is less than 4. So P itself is just a propositional variable. There are lots of different ways sometimes to express some particular assertion, but the assertion itself is kind of its own thing, right? So it is either true or false. So when we negate something, we are changing the truth value, right? Our statement was true, and we negate it. That negation of that statement is false. So the assertions themselves, at this level, at the level of propositional logic, they basically don't really matter. The only thing that matters is whether they're true or false. Was it Andrew that asked that question?
Yeah, that helps. Thank you.
Okay. All right. So now we've got and, or, and negation, and we have exclusive or, and we can start to build up more complicated statements. And just like in regular math, there's an order of operations that we follow. There is also that in this propositional formal language. And it's always best when it looks weird to use parentheses. So you have to remember, like PEMDAS, parentheses, exponents, multiplication, right, division, and then addition and subtraction. So there's that kind of order of operations for these that we've just written down. First is negation, and then is or. Another word for and is conjunction. Another word for or is disjunction. And if we have an order of operations, then we can build more complicated things, right? So I can write something like P and Q or R. And we can pick this apart and ask ourselves, is this a true statement or not, right? So the value of P might be 4 plus 1 equals 3. And the value of Q might be 2 minus 1 is equal to 1. And the value of R might be, this is a more complicated statement. And it says 4 plus 1 is 3 and 2 minus 1 is 1, or 6 is less than 7. And we can ask now, this is still an assertion, right? Is this true or false? Well, if I follow the order of operations, oh, sorry, somebody was going to say?
It should always be true. The proposition on the right, 6 is less than 7, is always true.
Mm-hmm.
So because the whole thing is separated with an or statement, and one of the prepositions is true, then the whole thing is true.
Yeah, so we have these two parts, and we know that when we use that symbol, that means, and we know that that means one or the other or both of these two, we call these disjuncts. As long as one or the other or both of the two disjuncts is true, then the whole statement will be true. So this one is true. And what about this one? This disjunct is false, right? So we have, if I break it down another way, 4 plus 1 equals 3, that's false. And 2 minus 1 is 1, that's true. Or 6 is less than 7, that's true. I can take this down another step. false and true, going back to that line of the truth table, that's false because and means both have to be true. Or that other statement is true. So now I have this false or true. And going back to that line of the truth table, let's see, I can take us back there. False or true. That's this line of the truth table. It tells me that that disjunction is true. Does that make sense? All right. So we have, in this, we have a particular example that is of this form, the P and Q or R. And we could actually build out an entire analysis of that statement that's going to tell us what is the truth value of P and Q or R going to be for all the various scenarios that could possibly happen. So I think maybe I'll write one example down like that, and then yeah, we'll call it a day. It'll be a good place to stop. So we have P and Q or R. So we want to consider all the possibilities of these three propositional variables. There are, you think about it, 8 different possibilities, because P could either be true or false, Q can either be true or false, and R can either be true or false. So that makes it have a bigger table. And so there are 8 possible combinations of true and false you can have for those 3 variables. And now what we want to do is evaluate this whole statement. But we don't have to do it all at once. Just like if you were going to compute x plus y times z, you would compute x plus y first, right? And then multiply it, whatever that number is, by z. So I'm going to compute the truth value of P and Q first. And let's see, P and Q means both P and Q have to be true, right? So that means that in these 2 rows where both P and Q are true, P and Q will be true. All of them, you can do a quick check, and all the rest of them will have falses. Those first lines of the truth table are the only place where we have both P and Q being true. Now, our proposition, I'm going to pick those 2 columns so I don't have to write them again. Our proposition looks like this: P and Q or R. So now I know, we've defined what the word or means. It means at least one of these 2 things is true. So now I just need to go through these 2 columns and look to see if at least one of those 2 things is true. Okay. So I've got both of them being true. We have a false and a true, true and false, false, false. Okay, that's going to be false. And then there are 2 other places that we're going to have a false. That's all I have to say for today.